Welcome, everyone. Thank you for joining us for today's webinar, What to Do After a Facility Siting Study, presented by Josh Bruce Black. Today's webinar is illustrative of our mission at Baker Risk to manage hazards and risks through high-value services, products, and research. At Baker Risk, we focus on 5 specific areas: incident investigation, loss prevention, testing and research, risk management, and the Baker Risk Learning Center. We invite you to visit our website to learn more about this. At our website, you will also be able to view and watch our previous webinars on demand. As a special note, to dig deeper into facility siting studies, we recommend you attend our July 20th 2-day course, FSS and QRA training. If you are interested, leave a comment in the Q&A box or visit our website. Now, for today's webinar, I want to go over a few housekeeping items. First, we have posted links to content related to our webinar subject in the chat box. We invite you to explore Baker Risk, published papers, previous webinars, and Baker Risk Training Center courses related to facility siting studies. Second, we want to respond to your questions following this webinar. Please type questions into the Q&A box and the presenter will respond to the questions. Finally, at the close of our webinar today, please provide feedback by responding to our survey. Now, let me introduce today's presenter, Josh Bruce Black. Josh is a principal engineer at Baker Risk and is located in our Houston office. Josh is experienced in completing facility siting studies, business interruption risk analysis, hazardous area classification studies, and other risk studies. He is a facilitator and trainer assisting industry leaders to understand the facility siting study process. Josh is a member of the API RP 752, 753, 756 Facility Siting Revision Committee and the National Fire Protection Association 59A Technical Committee. Now, without further ado, I will turn the time over to Josh Bruce Black.
Thank you, Naomi. I appreciate the introduction, and it's great to be speaking with all of you today on what to do after a facility siting study. So this webinar applies to both a consequence or risk-based facility siting study. However, I'm going to focus most of my discussion today on risk-based facility siting studies, also commonly known as quantitative risk assessments. One reason being that a natural next step to a consequence-based facility siting study with high or intolerable consequences would be a risk-based facility siting study. The initial next step after performing a facility siting study is to compare results to company or industry tolerance criteria to determine whether the facility siting study results are considered broadly acceptable, tolerable if as low as reasonably practicable, or intolerable. Facility siting results that are considered broadly acceptable do not require further analysis or mitigation. Results that fall in the LOPAs, or intolerable region, should initially be assessed using refined or more detailed analyses to reduce conservatism. However, results that still fall in the as low as reasonably practicable or intolerable region after refinement require mitigation or demonstration that results are a LOPA, meaning that the cost of risk mitigation is grossly disproportionate with the level of risk reduction. Lastly, I will discuss how inputs and results from a consequence or risk-based facility siting study can be leveraged to perform additional technical safety studies at your facility. So you may have a consequence or risk-based facility siting study, and refinement of the analysis and or mitigation can be performed based on the results of either study. But today, again, I'm going to focus more on risk-based FSS results, since a risk-based mitigation approach offers more options. Typical risk results are presented in terms of societal risk and individual risk. Societal risk is a measure of risk incurred by a group of people, while individual risk represents the risk incurred by an individual, independent of occupancy. Regardless of the risk-based facility siting study tolerance criteria a company has established, Once risk tolerance thresholds have been exceeded, the most straightforward and effective approach to identifying appropriate risk mitigation strategies is to start with a review of societal risk results. These societal risk results should be presented in tables with sources contributing the greatest risk and locations incurring the greatest risk at the facility. They should also identify the contribution of risk by hazard and be sorted from highest to lowest risk. And the reason for this is it provides the most straightforward and effective approach to identifying appropriate risk refinements and mitigation strategies. So let's take a look at some example societal risk results, starting with source societal risk results. You can see here it's a table with source societal risk results with the sources in the first column on the left, and then the risk contribution from each source broken out by hazard: explosion, flash fire, toxic, and jet pool fire, and then the total. And the risk from each source is sorted from maximum to minimum. So you can clearly see that in these results, source 01 contributes the greatest risk on site at 40% of the risk, and a risk of 3.4 E-4, which is predominantly from toxic hazards. Source 02 represents 29% of the risk on site, with a risk of 2.5 E-4, again predominantly from toxic hazards, followed by the boiler building fill case scenario, which is driven by explosion hazards and contributes 11% of the risk on site. So in this example, these three scenarios represent 80% of the risk on site, and is really where the focus on risk refinement or mitigation, if your risk tolerance criteria has been exceeded, you should focus on here. Looking at location societal risk results, this is the risk incurred at different locations on site by people in different buildings or outdoors, and the blue highlighting represents people outdoors in different outdoor areas. Again, the locations all identified in the first column, and then the risk broken out by hazard: explosion, flash fire, toxic, and jet pool fire, and then total, and sorted from maximum to minimum. So in this example, we have the laboratory incurring the highest risk on site at 34% and a risk of 3E-4, predominantly from toxic hazards. The office building incurring 21% of the risk on site, a risk of 1.8 E-4, again predominantly from toxic hazards, followed by the control room with 14% of the risk on site, a risk of 1.2 E-4, predominantly this time from explosion hazards. And these three buildings incur 70% of the risk on site. So again, risk refinements and mitigation strategies should focus on these locations, as this will drive risk down the furthest if we can refine or mitigate risk in these locations. Another way to look at location societal risk results is actually the sources contributing risk to each individual location. So here's an example with an admin building, and you can see the sources that account for the risk incurred at the admin building. So again, separated by hazard: explosion, flash fire, toxic, and jet pool fire in total, and sorted from maximum to minimum. So in this example, we have this ammonia source from C102 causing 27% of the risk to the admin building, predominantly from explosion hazards, followed by the crude P211 source representing 24% of the risk to the admin building, predominantly from jet pool fire hazards. And these two scenarios represent over 50% of the risk to the admin building. So again, instead of looking at potential refinements and mitigation strategies at the admin building, you could go back to the source and identify risk refinements and mitigation strategies associated with these sources, which would also mitigate and refine the risk to the admin building. So once you've looked over your risk results from your facility siting study, then you can start identifying potential refinement options. So when you have it laid out like this, it clearly identifies different refinement options. And I've categorized these potential refinement options into three main categories: source modeling refinements, building modeling refinements, and risk modeling refinements. And again, the idea here is to look at potential refinements that can reduce conservatism in the analysis. And I'm going to provide several examples within each of these groups. But again, this is not an encompassing list of potential refinement options. There are additional ones out there as well. So in terms of source modeling refinements, the first thing I would do is, again, review and look over high-risk sources. Look over their process conditions, make sure they're modeled as accurately as possible. The next step I would look at is more accurately representing high-risk parts of the process by potentially further segmenting high-risk scenarios. So when you do a typical study, you assess a certain number of scenarios. One scenario might include a vessel, some piping to a pump suction, and maybe even the pump discharge and out to a next vessel. And so if this was a high-risk scenario, you could take it and further segment it and say, I'm going to have a source from the vessel and the piping to the pump section. And I'm going to have another source at the pump representing the pump and the pump discharge to the next vessel. So to more accurately represent those high-risk scenarios at the plant. Another source modeling refinement that you could look at is that many facility siting studies initially utilize a conservative assumption of modeling an instantaneous discharge rate. So you could review high-risk sources and perform transient calculations based on inventory, blowdown, pump and compressor capacities, etc., to reduce conservatism. And an example of this is shown in the top left, where we have a blowdown curve with discharge rate with time. Another source modeling refinement you could do is review and create automatic detection and emergency shutdown capabilities throughout the process. And you have an example of an emergency shutdown valve in the bottom left. For explosion calculations, an important parameter is the material reactivity, which is typically based on the laminar burning velocity for pure materials and is based on the Le Chatelier's principle for mixtures. So since it's based on a principle for mixtures, you could actually test the mixture reactivity in a lab setting. And that's shown in the top right, where you have a chart of laminar burning velocity versus equivalence ratio, showing what is the actual laminar burning velocity of a mixture through testing. And testing in a broader context is just a potential refinement option. So it doesn't have to be just around material reactivity testing. You can test a lot of different things to more accurately then model them later in a facility siting study. Another potential source modeling refinement would be around the modeling of the dispersion calculations. So many facility siting studies, especially onshore, use free of fuel dispersion models, which do not account for obstacles and obstructions. So for high-risk scenarios, you could perform more detailed computational fluid dynamics modeling, which is shown in the bottom right, where we have on the left an example of volumetric concentration contours, and on the right, the external surface of the cloud, showing the external surface of the cloud. Moving over to potential building modeling refinements. The first thing I would do is review and revise structural modeling for high-risk buildings, for example, based on structural drawings, Or if you modeled the initial buildings based on potential building types, like a list of potential building types, you could go to a single degree of freedom type methodology and analysis to model those buildings more accurately. If you've already done single degree of freedom analysis and it was based on a site visit and measurements on site, if you do have structural drawings, you can more accurately model that building potentially. If there's rebar in it, what is the rebar size? What is that spacing? Which may not be, you may not be able to tell just from visual inspection of the building. Other potential building modeling refinements would be to do even more detailed structural analysis using multi-degree of freedom analysis, which accounts for the response of multiple components rather than just a single component at a time, and that's shown in the top left here. Or you could do finite element analysis, which models the response of the entire building with time, shown in the example shown in the top right here. For buildings with high toxic risk, especially shelter-in-place buildings, you could review and revise toxic modeling of those buildings based on leak tightness testing with blower door and/or tracer gas methods. An example of a blower door test is shown in the bottom left, and the results from a tracer gas test, where you put in a gas like carbon dioxide and measure the concentration decay with time within the building, is shown here. And another option for buildings with maybe high fire risk would be to review and revise fire modeling of high-risk shelter-in-place buildings based on fire dynamics simulator analysis, which is shown in the bottom right, where you can see a thermal radiation is applied to the building, and you measure the temperature rise inside the building with time based on the design of the building. Moving on to potential risk modeling refinements. Again, the first thing I would do is review high-risk sources in terms of their equipment counts, piping lengths, and make sure it's modeled as accurately as possible. Then you could do things like perform more detailed frequency calculations using fault tree analysis for specific scenarios like steam drum ruptures, furnace firebox explosions, runaway reactions, etc. And an example of a fault tree analysis is shown in the top left. You can also review equipment and piping for specific design considerations, things such as double-walled pipe, magnetic drive pumps, piping with minimal or no flanges, etc. And an example of a double-walled pipe is shown in the bottom left. You could review PPE availability, make sure it's adequately credited in the analysis, and HVAC isolation reliability, which is both shown in the top right. Or another option, a risk modeling refinement, would be to perform detailed analysis of loading and unloading operations based on the hose type, inspection and maintenance practices, shutdowns, etc., with an example of this in the bottom right. So once you've looked at potential modeling refinements that could be done, whether they're at the source, the building, or risk, and you've reduced conservatism, more accurately modeled those high-risk scenarios, if your risk still exceeds the intolerable or is in that ALARP region, as low as reasonably practical, and needs to be demonstrated, you can look at potential mitigation strategies. That's the next step of the process. And here I've divided mitigation strategies into two major categories: source risk mitigation and location risk mitigation. And I'm first going to talk about source risk mitigation, which is on the left, starting from the top going down. And so the first mitigation strategy is the elimination and reduction of hazards. And that's a focus of inherently safer design. So elimination and reduction in this context include things like reducing the inventory of the hazardous material or substituting the hazardous material in a process for a less hazardous or non-hazardous material. Examples of this risk mitigation measure would be like replacing chlorine cylinders for water treatment at cooling towers with bleach, replacing an ammonia refrigerant cooling system with a less toxic material, addition of dikes, remote containment and runoff systems, or even removal of out-of-service buildings and equipment. Moving on to release prevention as another mitigation strategy, this is about reducing the likelihood of a hazardous event from occurring. And a key aspect of release prevention is a thorough and realistic understanding of the potential causes of release from an individual scenario. So several examples of causes include startup alignment, improper lockout tagout, internal external corrosion, external impact, overfill, operator error, and design fabrication error. And while investing strategies that could mitigate a potential release from an external impact, consideration should be given to installing physical barriers, such as crash bollards, preventing personnel from lifting over operating equipment, increasing the depth of cover and visible signage for pipelines, for example. And for releases due to internal or external corrosion, you could do things like use an exotic metal material, have double-walled piping, or increased inspection. Moving on to detection and isolation, which is another potential mitigation strategy of flammable and or toxic releases, which focuses on reducing the quantity and duration of the release. So the effectiveness of this strategy depends on the reliability and timeliness of detection and isolation, as it is a collaborative effort, and one without the other would be ineffective. I'm going to save the water spray mitigation strategy discussion to the next slide, where I have an example and picture of it. So moving over to the right of potential location mitigation strategies, and starting from the top again, relocating personnel further from the process, consistent with safe and effective operations, is one of the guiding principles of API-RP 752 and 753. And this mitigation strategy is also reflected in the concept of hierarchy of controls with respect to location mitigation, with reducing occupancy and or increasing the distance between occupants and the hazard, considered the most effective location mitigation strategy beyond just eliminating occupancy completely. And the rest of these location risk mitigation strategies I will again talk about on the next slide with some visual examples. So starting on the top left, upgrading an existing building's resistance to explosion, fire, and or toxic hazards can be another effective mitigation strategy. Potential building upgrades focused on explosion risk mitigation include but are not limited to external and or internal upgrades, building encapsulation, and partial building upgrades. And in this visual on the top left, you can see examples of this with external upgrades with straps in the top left. Then we have external upgrades with posts. After that, then a shield wall of one of the walls of the building, I guess the reflective wall of the building, and then shield walls on all sides of the buildings, and then an encapsulation of the building with the roof and sides, and then an adjacent building on the bottom right. Moving down to the bottom left, we have a new building design, which should typically be considered as one of the potential building upgrade options or as an alternative mitigation strategy to upgrading existing buildings. And in the design of a new building for explosion hazards, consideration should be given to modular designs as well as a range of feasible construction types, such as steel frame buildings, precast concrete buildings, masonry buildings, etc. Should also consider things like the availability of materials and the time needed for construction. Moving to the top right is an example of the design of a new building for toxic hazards. And this is similar to upgrading a building for toxic hazards as well. And you should consider things like the emergency response strategy, whether it's shelter in place or evacuate, whether personnel are essential and required to shut down operations, and whether an internal room could be designed as a shelter in place location. And Bakeris has developed a best practice document for toxic SIPs that provides additional information on potential building design and upgrades focused around toxic risk mitigation. But in this example on the top right, you can see the risk associated with evacuation versus shelter in place associated with different leak tightnesses of the building, as well as HVAC isolation reliability. Finally, in the bottom right, we have examples of personnel protective equipment and a water spray system. And for PPE, for personnel protective equipment around toxic hazards, it's important to consider this if you do have toxic hazard on site and you don't have PPE, this isn't a potential mitigation strategy, is providing PPE, either a filtered mask or self-contained breathing apparatus, for example, for a certain duration. And if you do have PPE, depending on the quantity of PPE available, where it's available, maybe in certain locations or buildings, and what type of PPE is available. Is it a filtered mask versus a self-contained breathing apparatus? All of that can change the results for that mitigation analysis. For the water spray, this is important in the design of new buildings, as well, not for buildings, but a water spray system is a post-release measure to limit the impact of releases at the facility. Water spray systems include things like water curtains, fixed water monitors, portable water cannons, and sprinklers. And the picture on the right is an example of a water curtain. But directing water spray through a gas cloud has several effects, and the interaction between vapor cloud releases, air, and water droplets can be a complicated scenario to model and predict. However, there's extensive research that's been conducted around water sprays to mitigate dense clouds like hydrogen fluoride, chlorine, and ammonia, for example. So now that we've looked at potential refinement and mitigation options and examples, let's look back at the initial source societal and location societal risk results and look at what we would apply in these scenarios. So again, here in this example, we have source 1 and 2 contributing the highest risk on site, predominantly from toxic hazards. And then we have the boiler building field case scenario as the third highest risk on site, predominantly from explosion hazards. So in terms of the toxic releases, if we look at the prevention of the release, we would look at things like maybe installing crash bollards to reduce external impact, minimizing flanges or using double-walled pipe around the piping around these toxic releases. Potentially maybe using, if it's a single seal pump, a double sealed pump or magnetic drive pump. Things of this nature would help prevent that release from occurring. Moving on to detection and isolation of the release, you would look at, well, is detection and isolation available right now? Is there toxic gas detection in the area? Are there isolation valves? Are they manual or automatic? If they're manual, could we make it automatic? If there is some detection or no detection, can we add additional detection in this area? Things of that nature. For water spray mitigation, would it be effective for these toxic materials? Is it available? Is it in the right locations? Could we add it? And if, say, these toxic scenarios were around loading and unloading operations, potentially, should we enclose, filter, and or direct the release to an elevated stack rather than allowing dispersion out into the free field? For the boiler building field case scenario, for prevention of the release, I would look at, this is around the natural gas piping to the boiler. So how much is that piping inside the building? So can it be minimized at all and just travel a shorter distance to go outside and travel outside rather than inside the building? Are there flanges? If there are, can we minimize flanges? For detection and isolation of the release, is there flammable detection and shutdown capabilities right now? If there are, can we add more, increase the detection, put more detectors out there? If it's manual shutdown or there aren't shutdown systems, can we add those? Around boiler fill case scenarios, the idea is that you can have an internal release that could fill this building volume and result in an internal vapor cloud explosion. So could we sectionalize the building and make the volume smaller at all than the entire building volume? Could we make it, constrain it to a single room, for example? Or even a better option could we put this boiler outside? Could we reduce confinement around the boiler? Could we open up the walls and the roof? Or if we need a roof, could we at least take out all the walls around the boiler and not have the potential for an internal vapor cloud scenario? Moving on to the location societal risk results. So looking back at this, we can see clearly that the laboratory, office, and maintenance buildings incur the highest risk from toxic hazards, while the control room incurs the highest risk from explosion hazards. And so looking at potential mitigation options around these buildings, for the laboratory, office, and maintenance buildings driven by toxic hazards, I would look at what is the current emergency response strategy? Is it evacuation or shelter in place? And should it be changed? If it is shelter in place, how is the HVAC system isolated and how leak tight is it? Could we make it, the isolation system more reliable? If it was manual, could we make it automatic? Put detection and automatic shutdown of the HVAC system? Could we reduce the leak tightness of those buildings? I'd also look at what personnel protective equipment is currently available. Is there anything available? And if there is, what is it? How many are available? What's the reliability of that? Could we make it more reliable? And finally, I would look at, are there challenges to the sheltering strategy? And for the laboratory and maintenance building, there likely are, because the laboratory building, you may have ventilation hoods and things that need to be running in a high HVAC turnover rate. Can you isolate that HVAC system in a timely manner at all? For the maintenance building, you probably have overhead doors and large openings, and so that may minimize the effectiveness of that shelter-in-place strategy. For the control room, which is driven by explosion hazards, I would look at what type of upgrades could be implemented, what is the cost of those upgrades and the impact on operations, and look at how does that cost compare to the cost of a new control room. So I want to note that the applicability of each refinement and mitigation strategy is dependent on a specific facility's source and location risk results. And an effective refinement or mitigation strategy for one source or location does not mean it is an effective refinement or mitigation strategy for all sources or locations. So risk refinement and mitigation must be assessed on an individual source or location basis. It's a different concept than a process hazard analysis or layer of protection analysis, where adding the same independent protection layer at every facility may provide an order of magnitude risk reduction, regardless of the facility location. So I have found that a useful approach to effective refinements and mitigation strategies, to identifying effective refinements and mitigation strategies, is to brainstorm potential options in a workshop type setting that allows from contribution from knowledgeable site personnel, like operations, maintenance, I&E, etc., as well as external knowledgeable and experienced resources. So in summary, utilize your facility siting study as a resource to identify potential risk refinements and mitigation strategies, and to make informed and effective mitigation decisions. So I'm going to shift gears just a bit right now, as I also want to discuss how you can leverage your facility siting study to perform additional safety studies. And this figure provides several examples how you can leverage your inputs and results from your facility siting study into other studies, but it's no means an all-encompassing list. So kind of at the top top right, we have consequence and risk-based building design and leak tightness shelter-in-place design. And so those are the pretty obvious ones, I would say, and ones that we really have already covered. So we're not going to talk any more about those right now. And moving down to the kind of the bottom left, you have pressure relief and flare analysis. And so with this study, you could actually model your atmospheric PSVs, you could model different flare scenarios, like flare flame out scenarios, in your facility siting study model that you've already built to look at the effect, if there is any, on occupied buildings, on people outside, on elevated platforms or different areas where people could be working, to see if there is an impact, especially maybe over time where the plant has changed. And it could affect new things now. For emergency response planning, again, you can look at things like where your muster points are, where should they be? Should they be relocated? Should you have more potentially? You can also look at things like, of course, whether you should evacuate or shelter in place for different hazards, toxic or fire hazards, for example. For hazardous area classification studies, a lot of the inputs in a facility siting study in terms of the process conditions, material, location of equipment, and things like that can be leveraged to now look at where are my hazardous area classification boundaries in terms of Class 1, Div 1, Class 1, Div 2 boundaries, for example. And I'm going to talk about additional of these technical safety studies in greater detail on the next couple of slides here. So starting with process hazard analysis and layer of protection analysis, PHAs, HAZOP, LOPAs, you can utilize the dispersion, the flammable and toxic dispersion distances, the thermal radiation distances predicted in your facility siting study to align the PHA team on the consequences of potential PHA scenarios. So for example, if one of the PHA scenarios was a release from a pump seal, you could look at the flammable dispersion distances from that pump seal or the toxic dispersion distances from that pump seal to look at, okay, this goes to the lower flammability limit, it travels 50 feet or 100 feet. And so now everyone on that PHA team is aligned on what that hazard boundary, what that potential release could go to. You could also, if you have multiple facility siting studies at different facilities around the country or the world, you could actually create internal PHA lookup tables with all this information to, again, help align the PHA team on the consequences of scenarios. Moving on to asset damage and business interruption risk. You can basically, the facility siting study is looking at the vulnerability and the risk to people. So now I can take those same type of scenarios, the explosion and the fire scenarios, not look at the vulnerability and risk to people, but look at the vulnerability to equipment and to the asset and the risk of business interruption. So, I can look at things like, what is the vulnerability to, very valuable pieces of equipment at the plant, or to fire water pump houses, or motor control centers and substations, things that are of critical importance to keeping that plant operating. I can take it a step further and calculate business interruption risk, accounting for things like downtime, product loss, lost revenue, and other operational interdependencies. And you can create risk results just like a facility siting study, where now I'm looking at what is the risk incurred at different buildings and equipment from business interruption, and what are the scenarios that are contributing the greatest risk to business interruption. And so it's that same type of results to identify where should I focus my efforts on refining the risk and then mitigating the risk if necessary. Another way you can use your facility siting study results and inputs is in fire and gas detection mapping. So you can use the flammable and toxic dispersion distances you've calculated, the thermal radiation boundaries and contours to look at the coverage of your actual fire and gas detection systems in the plant. Look at the percentage of scenarios that would be detected. You can also take it a step further and look at the frequency of those scenarios if you have a risk-based facility siting study, and prioritize the high-risk sources and optimize placement and number of detectors based on those high-risk sources instead. And finally, you can also utilize your jet and pool fire thermal radiation predictions to look at fire hazard and mitigation analysis. So you can look at those scenarios and quantitatively determine your maximum fire water demand, your fire water coverage, whether you have deficient passive fire protection, and you can also optimize placement and number of monitors deluge during the design phase of projects. So in summary, how can we help? Well, we can help you identify, develop, and implement practical risk refinement and mitigation strategies. We have an experienced and integrated team of consultants in fire protection, hazard identification, risk analysis, and loss prevention. And we can help you leverage results from your consequence and risk models to perform additional technical safety studies at your facility. So with that, I will turn it over to questions.
Thank you, Josh. I'm going to go ahead and ask some questions that did come up during the presentation. And just as a reminder, if you have not already done so, please be sure to type your questions into the Q&A box in your control panel. So Josh, first question is, for source mitigation, how do you handle verifying benefits of providing emergency block valves in risk reduction in cases where a scenario is contributing threat case for an occupied building?
So with emergency isolation valves, a lot of times, hopefully we're talking about like automatic isolation valves. So, oftentimes manual type valves where someone has to go do something in the field or view something and then isolate it. That can take time, and so is not something that I would say is typically credited in risk mitigation or in a facility siting study. But for automatic isolation, again, you can look at things like what is the timing of detection of either the gas detection system initiating those automatic isolations, or is it process deviation? What would the timing be? How long does it take to close the valves? And then, how much material are we talking about between the valves that could be released? And so you could do things like model that that would be a transient calculation instead of that instantaneous discharge rate, and look at over time how much material, how long is it there, and credit that. Instead of saying the release could go on for a longer period of time, it's minimized because you have those emergency isolation valves, and so you've shut down, you've reduced your discharge rate with time, and so you can look at that and credit that in the analysis, with either ignition probability, with the consequence. You could model multiple consequences, not just that conservative instantaneous release rate. So there's lots of ways that you can tweak things in the model to credit automatic emergency isolation valves like that.
Perfect. Next question. For refined modeling, is the facility siting study updated once the CFD modeling is completed?
Yes. So the idea in a lot of this would be, even if you're using somewhat external programs or more detailed analyses, is to actually, take those results and put them back into, your facility siting study that you have. So with computational fluid dynamics, you would try, cloud volumes. Where is the cloud? If it maybe was a internal vapor cloud explosion scenario within a building or something like a compressor building, it would be looking at, okay, what is the size of the cloud in that building, and what's the volume of it, and then representing that back in the facility siting study in the best way that you can.
Thank you for that. Next question. Would water spray mitigate risk of explosion of a vapor cloud, or would it be negligible?
Yeah, I would say that potentially water spray could help mitigate a flammable release, but it's not as studied or as I would say generally people do not credit water spray with flammable releases. And we have tested this somewhat at our test site as well. And the idea is that while it does, you do have mixing and it does reduce the flammable concentration maybe close at the source, it also can actually extend the actual flammable cloud because it's mixing now. And so it actually could be flammable in places, further downwind than it was initially. So there's different effects. And so I would typically say water spray is most effective for some toxic materials like HF, ammonia, and those things. But really, maybe water spray could be credited with things like in your, obviously fire and mitigation analysis where you're kind of trying to cool down vessels and things like that, but not, it's not as clear exactly the effect on flammable releases and how valuable it is. So.
Okay, and this will be the last question before we conclude this presentation. Can you discuss the differences between consequence-based versus risk-based FSS?
Yeah, so just at a high level, a consequence-based facility siting study, looks at the consequences from explosion, fire, and toxic hazards. So, and looks at really the damage to buildings from explosions, the vulnerability to people in those buildings and locations. Where a risk-based facility siting study looks at, also accounts for the frequency and the number of people in those different locations and around the facility. So now it's looking at the likelihood of those scenarios and not just saying what is the consequence of those scenarios.
Perfect. Thank you, Josh.
All right. Thank you.
So everyone, we appreciate you guys joining our webinar today, and we look forward to seeing you at our next one on September 7th. As a final reminder, today's webinar will be posted to the Baker Risk website, and we ask that you complete the survey at the conclusion of this webinar. If there are any other additional questions, we ask that you reach out to Josh directly. But until then, we thank you again for joining us, and we'll see you next time.